Students, good morning. Today I am going to discuss about the reversible adiabatic compression. This class comes under the category of applications of thermodynamics to flow process. Applications of thermodynamics to flow process. Applications of thermodynamics to flow process. Today, in this category, pumps, compressor, nozzles, all those things can be discussed. In today's class, I am going to discuss about the compressor. Compressor is a device used to compress the gas or air, or used to increase the pressure of the working fluid, air or gas, from a given pressure to desired final pressure. Clear? Okay. Compressors are two types. One is reciprocating compressor, another one is turbo type or centrifugal type compressor. Reciprocating type compressors are used to high pressure, but unfortunately it provides low volumetric flow rate. While you go for turbo type compressor or centrifugal type compressor, it gives high volumetric flow rate, but unfortunately it provides low pressure. Clear? These are all the small information regarding compressor. What is going to be compressor? What are the types of compressor? Why they are two different types? Okay. Now I am going to discuss about the reversible adiabatic compression, that too in flow process. In my next class, reversible isothermal compression. This is the first class, right? What is the first law of thermodynamics to flow process? First law of thermodynamics to flow process. The mathematical representation is of m del v square plus mg del z plus del h is equal to q minus ws. This is the main equation of first law of thermodynamics to flow process. In process industries, the contribution by kinetic energy as well as contribution by potential energy are assumed to be negligible. So the final form of the equation is del H is equal to Q minus Ws. Clear? This is the equation to discuss reversible adiabatic compression process. Clear? This is the main equation. Okay. Since this is the adiabatic process, the heat content in the system Q is equal to constant. Hence, changes in heat content is equal to 0. The compressor is perfectly insulated. There is no way to exchange its energy or heat content from system to surrounding or surrounding to system. The compression process or compressor is highly insulated. This is the adiabatic compression process. dq is equal to 0. For adiabatic compression process, this equation becomes del H is equal to minus Ws, or I can write Ws is equal to minus del H. Clear? Minus del H. See, this is the reversible process. This is the reversible process. The compressor needs certain amount of energy or work to compress the air or gas from initial pressure to final pressure. The work is called as shaft work. This is called as shaft work. Clear? Right. Since this is an adiabatic process, the energy should be utilized to compressor to compress the gas is from its internal energy or enthalpy, decrease in enthalpy. Clear? Process is reversible. Moreover, it is adiabatic. Hence, this reversible adiabatic compression is also known as isentropic compression. Isentropic compression. Isentropic compression. Hence, I used S as a suffix. S stands for entropy. S stands for entropy. Clear? Reversible adiabatic compression. Adiabatic means there is no exchange of heat between system and surrounding. Reversible means the amount supplied to the compressor is completely utilized for compression purpose. Hence, in a reversible process, the changes in entropy become zero. Del S is equal to 0. When changes in entropy is 0, that means entropy is constant. Entropy S is equal to constant. When entropy is constant, the process becomes isentropic process. Hence, this reversible adiabatic compression process is also known as isentropic compression. Right. Coming to the point of shaft work. The shaft work is nothing but isentropic work. Isentropic work. Isentropic work means the minimum amount of work, because it is a reversible process. Because it is a reversible process, isentropic work means minimum amount of shaft to work required for a compressor to compress air or gas from a initial pressure to its final pressure. Clear? Isentropic work is nothing but it is a minimum amount of shaft work for a compressor to compress air or gas from a initial pressure to final pressure during reversible adiabatic compression or isentropic compression. Clear? Okay. An equation. What next? Estimation of this shaft work. This shaft work estimation has three different ways. The shaft work estimation is three different ways. First method. Method 1. Right. What is the base equation? Shaft work is equal to Ws is equal to minus del Hs. Clear? Del H is nothing but Cp into dt minus of Cp dt. This is the difference in temperature. While you compress the gas, definitely the temperature will be increased. Initial temperature to final temperature. So dt is nothing but it is the difference between final temperature to initial temperature. So minus Cp into T2 minus T1. Clear? Okay. What about Cp? Heat capacity under constant pressure process. Heat capacity under constant pressure process. Okay. Cp minus Cv is equal to R. Cp minus Cp by Cv is equal to gamma. R stands for gas constant. Gamma stands for heat capacity ratio. Now I am going to replace this Cv instead of Cp. Cv in terms of Cp. Okay, Cp by gamma is equal to Cv. Substitute this Cv here. So Cp minus Cp by gamma is equal to R. After rearranging this equation, Cp into gamma minus 1 divided by gamma is equal to R. This equation provides Cp is equal to gamma divided by gamma minus 1 into R. Substitute this into here. Okay, eliminate this negative sign. Eliminate this negative sign by interchanging T1 minus T2. Instead of Cp, I am going to write like this: gamma divided by gamma minus 1 into R into T1 minus T2. Shaft work or isentropic work. This is method 1. This is the equation to estimate the shaft work for reversible adiabatic compression process. This is method 1. Okay, what next? Next method. What is the base equation? Del H is equal to W S is equal to minus del Hs. So this is the first method. From this method I am going to derive the second equation. So Ws is equal to gamma divided by gamma minus 1 into R T1 minus R into T2. Clear? R T1 R T2. PV is equal to nRT. For 1 mole of gas, PV is equal to R into T. Clear? P1 V1 is equal to R into T1. Similarly, P2 V2 is equal to R into T2. Clear? Instead of R T1, I am going to substitute P1 V1. So gamma divided by gamma minus 1 into P1 V1 minus P2 V2. Clear? For rearranging this equation, for simplification of this equation, I am going to multiply and divide by P1 V1. Gamma divided by gamma minus 1, P1 V1 divided by P1 V1, P1 V1 minus P2 V2. Clear? There is no changes in this equation. Only I am multiplying and divided by same P1 V1. So this equation becomes gamma divided by gamma minus 1 into P1 V1. I am going to take P1 V1 inside. P1 V1 divided by P1 V1 minus P2 V2 divided by P1 V1. Clear? This equation becomes shaft work Ws is equal to gamma divided by gamma minus 1 into P1 V1 into 1 minus P2 divided by P1 into V2 divided by V1. In this equation, I am going to eliminate this V2 by V1 in terms of P2 by P1. Clear? Right. For an ideal gas, or in a polytropic, in the adiabatic process, the relationship between pressure and volume PV power gamma is equal to constant. This equation becomes P1 V1 power gamma is equal to P2 V2 power gamma. So P1 by P2 is equal to V2 by V1 power gamma. Or this equation gives V2 divided by V1 is equal to P1 divided by P2 power 1 by gamma. 1 by gamma. Now I am going to substitute this information in this equation. Shaft work is equal to gamma divided by gamma minus 1 into P1 V1 into 1 minus P2 divided by P1 power 1. Instead of V2 by V1, I am going to write P1 by P2 power 1 by gamma. P1 by P2 power 1 by gamma. See, this is P2 by P1. This is P1 by P2. I am going to inverse this content. Hence, shaft work Ws gamma divided by gamma minus 1 into P1 V1 1 minus P2 divided by P1 power 1. P2 divided by P1 power minus 1 by gamma. So after simplification, this equation gamma divided by gamma minus 1 P1 V1 into 1 minus P2 divided by P1 power gamma minus 1 divided by gamma. This is the second equation used to estimate the shaft work or isentropic work. Equation number 2. Clear? In this equation, the initial pressure and final pressure will be given in your question paper. Check what about the initial volume. If initial volume is given, it is okay. Otherwise, in your question paper, volumetric flow rate of gas or air will be given. Instead of initial volume, you can use the volumetric flow rate of air or gas. There is no problem. Clear? This is equation 2. What about the equation 3? See, this equation P1 even. For an ideal gas, P1 V1 is equal to R into T1. Hence, this equation can be rewritten like this. Shaft work gamma into gamma minus 1 into RT1 ln 1 minus P2 divided by P1 power gamma minus 1 divided by gamma. This is the equation number 3. In this equation, instead of P1 V1, I am writing RT1. That's all. This is the equation 3 used to estimate the isentropic work or minimum shaft work required to compress the air or gas from initial pressure to final pressure. Clear? Thank you.